Well, hi, good morning, everyone. I'm Tian-Xia, and I'm a PhD candidate at TU Delft in the Faculty of Architecture. And I'm part of ABLE Lab, which is the one lab in the 24 AI labs across TU Delft in different faculties. We aim to use AI to solve different domain problems. And our lab aims at using AI to help us address the societal challenges in the built environment, such as energy transition and circular economy. So we aim to answer two research questions. How can we use AI to support the deliberation and decision-making in multi-actor settings in a more responsible and transparent way? And second, how can we use AI to support the individual behavior change? So my PhD research is about develop a human AI deliberation system to help the different stakeholders make circular strategies in the transition. And specifically, I'm trying to combine domain knowledge with large language models so as to support the more responsible decision making. So today I'm going to present about a latest project of our lab, which is Collaborate AI for Housing Design. And I'm collaborating with 4 master students in our lab. And yeah, so the goal of the project is not to automate the design process using AI, but use it to collaborate with human beings so as to support a more human-centered design. And the traditional design process is now facing severe challenges, such as it's quite labor-intensive and time-consuming. And now it's even more challenging because our design requirements are much more complex, such as we need to deal with modularity, sustainability requirements, and also circularity, for example. And also, we are shifting to a more human-centered design way, which means we need to incorporate the preferences and values of the residents or users from the buildings into the design process. So that's why we propose the collaborative AI approach, which means that we want to develop an AI system which can understand human beings in a more semantic way. And also, we wanted to also interact with human beings so as to more collaboratively design the built environment to serve the purposes of the users. Well, basically, we try to use floor plan design as our use case because firstly, it's a common task. And secondly, we have a lot of open source data we can use. So in this research, it's divided into 3 parts. Firstly, the users can input their constraints and their preferences, and then the system will help them design the layout in the graph representation. And based on the graph layout, it will finally generate more realistic floor plans with more precise spatial configuration. But it's also parametric. So, well, and the users can actually interact in every steps so that they can incorporate their preferences to make the results more aligned to their values or their preferences. So the contribution of this research is firstly, it's interactivity in different steps based on graph representation. And secondly, it's interoperable because it's parametric based. So it's compatible to other computational design methods and also other parametric design methods, such as in BEAM. And also, we try to use AI to help us boost the creativity and help the users to design their homes. So there are actually a lot of research in generative design, especially in floor plan design. But most of them are end-to-end and image-based in the past, which means that they do not actually understand the housing designs as designers. They only understand it as the patterns of colors. So they try to mimic the color patterns. And some researchers are trying to use graph representation. In housing designs, most of them are trying to extract similar designs from the databases instead of generate them, which makes them less flexible. And in our research, we try to combine graph neural networks to generate the layout graphs directly, and also try to use generative adversarial neural networks to generate more realistic floor plans based on our layout graph. So we contain 3 steps mainly, and I will go through them. This is the overall framework of this methodology. The top part is the design process of the designers and also the user interaction with the AI system. Basically, the designers, they can input their preferences and their constraints. Then it will generate the layout graphs to represent how the room arrangement and the adjacency relationships between rooms. Then they can evaluate if the results fit their needs, and they can always modify the result based on their preferences. If they are satisfied with the layout arrangement, we can further generate the floor plans using GANs. And they can also modify the end floor plans result. So from the model part, we use DGMG, which is a graph-based generative model to generate the layout graphs. And we try to use relational constraint generative adversarial neural networks to generate the floor plans with more realism and spatial configuration of different rooms and components. So concerning the user input, we actually, the users can input the existing boundaries of their rooms, and also maybe they have some existing rooms they cannot change, which happens a lot in the renovation design cases. They can also input that into the system. And also they can input their preferences of different rooms and even the adjacency relationship of rooms, such as I want my living room just next to my garden and connected to my bedroom with a door, something like that. And it's not limited to this input, and you can always incorporate other inputs if you have more training data. And the second step is try to generate the layout graph based on the constraints the user provide and also the preferences of the users. So basically in this step, we try to use graph generation models to generate the layout graphs, such as we will generate the rooms as nodes and their adjacent relationships as edges, which contains their connection type, such as, and the model basically works in a way that it will decide if it need to generate more rooms and more adjacent relationships until it fits our needs. And if we are satisfied with the layout graph, we can proceed to the floor plan generation. Basically, it will do some message passing through graph neural networks and try to aggregate the semantic information in the layout graph to the different node attributes. Then it will do some deconvolution to expand the attribute to 3D volumes so that we can finally add a bounding box to the volumes of different room nodes, which represent its size and very precise spatial locations. Then in the end, we will render it into floor plans which designers are more used to. So this is a simple demonstration of the whole pipeline. So right now we only have the text-based input interface, but we will develop more graphical and user-friendly interface in the future. This is a generated layout graph you can see, and users can always modify or interact with the results based on what they want. For example, if they want another room node, they can always add it to the result. And it also provides different alternatives for the users to choose from. And if they are satisfied, they can proceed to generate the layout graphs, which is in parametric representation, but we will render it in images so that people can easily understand it. And they can also interact and change the floor plans in the end. So we evaluate our models using validity and novelty and quality of the design. So concerning the validity, we evaluate based on very simple hard constraints, which is not very complete. And for the floor plans, we evaluate if it fits the graph layout we input to the system. And novelty, we basically compare if it's different from the existing database, if it generates real new designs. Concerning the quality, we're now just using very standard realism matrices from computer science to evaluate if the floor plan is realistic enough. And this is the result from the layout graph generation. We can see that the fifth criteria is actually the bounding relationships of the rooms. It's hard for the deep generative models of graphs to capture all the precise spatial relationships between the rooms. So it's kind of challenging for the model now. And we evaluate the floor plan generation based on realism. So it's quite standard. So as we can see, we have some limitations in this research. Firstly, that we didn't evaluate in a more complete way. And second is that we can see that the generation result of the layout graph is not perfect. And third is that we can see a lot of propagation errors in the not end-to-end model. If the layout graph generation has some errors, then it will be more errors in the floor plan. So the future research will be, firstly, we will evaluate using more complete architectural quality matrices and also incorporate user study. And then we will try to integrate it with more computational design method to fix the result and to see how they can complement each other. And third is that we try to apply it to more realistic scenarios, such as circular design. So the main takeaway is that the contribution of this research is, firstly, we design more interactive process, which means the system can understand human beings in a more semantic way, and so that we can collaborate with it. And secondly, we make it more interoperable with other design methods, which is parametric based. And third is that we try to boost creativity by introducing deep learning models and try to bridge the gap between learning-based models and domain knowledge-based semantic representation of designs. So that's all. Thank you.